My name is Chelsea Mahaffey, and for my presentation, I'm doing a quick demo to help explain the rocket equation for launch. To first understand the rocket equation, we need to know Newton's second law, which is that force equals mass times acceleration, and that acceleration is the time derivative of velocity. We know that thrust is the main mechanism in a rocket's launch, so if you apply this law to thrust, it should follow that the mass of the rocket's exhaust times the exhaust acceleration is equal to the rocket's mass times its acceleration, but that isn't quite true, and I found a simple experiment to show why. Here I have a balloon acting as a rocket to demonstrate a rocket's launch, where air in the balloon is like fuel. The first form of Newton's second law assumed that the masses were constant, but as you can see, the balloon rocket lost mass from fuel, or in this case air. Instead, we want to use the differential form of Newton's second law, which accounts for both the changing velocity and changing mass. After you solve that differential equation, you get that the change in velocity of the rocket is equal to the exhaust velocity times the natural log of initial mass over final mass. Chapter 6 goes on to explain the rest of the rocket equation. This next video demonstrates how with no thrust, the balloon falls to the ground because of the gravitational force acting on it. Then the next video shows that if I push down on the balloon, it slows down towards the end of its fall due to the drag force. In the case of a real rocket though, air resistance wouldn't be nearly as strong as the force of gravity. Finally, these forces are all combined to make the final rocket equation. This equation also includes effects from steering and the Earth's spin, but they aren't as significant as the ones I already discussed. In the equation, the direction of space is taken to be positive, so any component opposite of that direction is negative. The part of the equation in blue is what we previously saw as the simplified rocket equation for a rocket in space, but the red components complete the rocket equation for launch.